Good. It's a pleasure to be here, and congratulate Hennig et al. For having a workshop purely devoted to 2D crystals, because in the past, these workshops and courses started in the 70s with EMBO courses that were focused on helices and things like that, and I was only involved in running one in 1982. We decided to focus it on 2D crystals. And there was a review published by Linda Amos and Nigel Unwin and I then. And then we stopped doing it. It went to EMBL. And then they gradually increased these courses to cover everything. Single particles, helices, 2D crystals, tomography. So then the whole approach and the emphasis became spread out and was very superficial and very thin. So it's great to have a course focused entirely on 2D crystals. And I guess this is the second or third one that Hennig has been involved in running. So the title here is Hennig's title, because I think the idea was to divide up the topics in the course so that you could focus on each segment of what's involved in recording, processing, and interpreting images of 2D crystals into the different steps. So the idea was that I should cover only processing of the images in 2D. And so what I've done is to say, what are the 5 main steps? And obviously there are many varieties, and Holger's overview on all the algorithms shows how creative people are being nowadays in tackling different specimens. But the idea here was to say, what are the 5 main steps after you've acquired the images? And of course, there's lots of work needed to be done before you get your images. But once you've got them, in between that and interpreting your map in terms of atoms or symmetry or docking or whatever, what are the steps? So one is you have to do computer processing of these individual images. And then once you've got images from all sorts of different angles, you have to put them together to make a 3D map. You may, if you're lucky, have crystals good enough to be able to do electron diffraction. So then you'd be recording electron diffraction patterns. And these are the programs that we wrote originally, and I have to say I don't know what's happening now with processing electrons, but you'll hear at this course. And then they have to be merged. Again, we had a program that Tom Seska wrote and improved for merging the electron. Then the results of the image processing, which is mainly phases but includes also amplitudes, and electron diffraction, which is only amplitudes, are then combined together. Lattice lines are fitted in the continuous Z direction, and then you calculate your map, and then you're into interpreting the map. So that was an overview of what we used to think about how it was involved. But today I'm only going to talk about processing individual images in 2D. They could be tilted images or untilted. And the approach that we took originally was that it was very important for the person doing the work to know how well they were doing. In other words, it's easy just to throw it into the computer and then something comes out, but how do you know it's right? How do you know that this way of doing it is better than that way of doing it? So our approach always was to try and create really nice ways of looking at it so that you could just run your computer program and then look at the output, and it would tell you something enough for you to make a judgment as to whether you were doing it right or well, and whether another way of doing it was better or worse. And then to have concise summaries. And with all the images and all the data and tilted and so on, you can easily get lost in the details and think you're doing well, whereas actually you might have got the space group wrong, you might be doing it badly and so on. So the sort of overall philosophy was to have easy to understand graphical plots that gave you an intuitive feel how well you were doing, and then concise summaries so you can get an umbrella overview as well as the nitty-gritty detail of what is this particular defocus or astigmatism and so on. So most of what I'll talk about are to do with this. So this is a sort of flow diagram from a paper in 1990, which was associated with a 3D structure of Bacteriodopsin, but it has in it more or less the complete philosophy. So the idea is you take your raw densitometered image or digitized image if it's from a solid state detector, and obviously the bigger the crystal, the better, the more unit cells and so on, and you Fourier transform it index it, get roughly, your parameters, so that you know where the crystal is, and then mask it off so that you're doing some averaging. Otherwise, it's a very noisy image. And then once it's masked, you've got a masked filtered Fourier transform, if you like. You cut out a little bit from the middle of that, which is a representative area of the 2D crystal. Maybe say if it's 6,000 pixels to start with, it might be 300 or 400 pixels square. So a few dozen unit cells, and then that would be Fourier transformed again. So now you have the Fourier transform of the raw image with some filtering to get rid of the noise, and then the Fourier transform of a reference area in the middle of that image. And these are cross-correlated together using this convolution reciprocal space method, whereby you multiply the Fourier transform of one of the images with the complex conjugate of the Fourier transform of the other image, and then back transform that to give you the cross-correlation map here. So that shows you peaks where your reference area, let's say the best bit of your crystal that was in the middle that you've chosen previously, perhaps by optical diffraction or computer diffraction, and then we had a program for searching this map of cross-correlation peaks called quad search, which gives you then a list of all the unit cells in your image, and that list is described in terms of deviations from the lattice that you'd indexed in the initial indexing up here. And then the original image then is reinterpolated, unbent if you like, to make all the unit cells agree perfectly with that originally indexed lattice. So you then have an unbent image where all the unit cells are exactly on the right places. You then Fourier transform that, and you look at it, and you've got all sharp spots. So you've gone from what might be a somewhat deformed crystal, and the extent of the deformation obviously is limited, and then if it's too bad, you might have to go to single particle and so on. So it was the software was written to do some unbending, but obviously it runs out of steam if that is too big. And exactly where that is, you have to judge. So you then read off in that Fourier transform the amplitudes and phases, and that bottom pattern here was merging them into let's say a projection pattern. And then in this paper, we were dealing with what happens when you tilt. You take tilted images, and where the contrast transfer function is varying as you go across the micrograph, possibly by a micron of defocus. It might be 1 micron defocus in one edge and 2 microns at the other edge. So we had these programs, TT-Box, which rather than just reading off the amplitudes and phases, which was a program called MM-Box, which was just M by M pixels, it does that at the same time as it corrects the CTF. So you end up there with properly corrected amplitudes and phases that you can just then calculate a map with. Then, of course, you've used an area from the middle of this micrograph, and it was also a noisy part of the original image. So you've done your best in a single pass through the image. But if you then take this unbent image and take it right back round to the beginning again, and then filter that with a smaller diameter holes, a smaller mask, so that you're getting greater averaging, that reference image that you started with, which was only maybe less than 1% of the area of your complete image, your reference area after being unbent and refiltered is then the average of the entire image. It's an almost noise-free reference image. And you can then plug that back in, and in later passes, you get much cleaner cross-correlation maps. You can unbend it again. In the second pass, then, you're doing almost as well as you can. And, of course, you can carry on doing this until you feel that there's no improvement. And I'll show you a little bit later about how we judge that improvement. And then if it's a tilted image, that's what these black box programs, we had TT mask. What that did was to correct either the raw image or the unbent image so that the amplitudes and phases of the Fourier components, instead of being varying as you go across the direction of increasing height in the image, the amplitude and phases had been corrected to be like they would be in a sort of in-focus image, if you like, that hadn't been affected by the contrast transfer function. And these could then be, in this 3D, you could then put them together, and you needed more passes because you were refining not just the lattice parameters and getting the noise down. You'd also be improving your knowledge of the defocus and the astigmatism so that you get your unbent, defocus corrected, tilted image to be a better representation of the real structure. So that was this extra arm of the flow diagram was added when we had it with the tilted transfer function correction and in 3D. And then the final thing, which is this asterisk here, later on, so probably about the year 2000, for only one project involving halorhodopsin, where the images, the crystals were very poorly ordered and rather noisy and so on, Edmund Kunji came, and we had this program, which I think Antje is down to talk about, called MakeTran, which is that you take your fully calculated 3D model of the structure, which has been derived from, say, 10, 20, or 100 images that have all been processed using the single image processing software. You then have a 3D model of the structure, and MakeTran then produces an image that is just like the image that you recorded in the microscope, but it's making the image from the 3D model, so that instead of the reference area now being a small area from the original micrograph, so 1% of the micrograph, or being the average of the whole micrograph, the reference area is now produced from the information that you've gleaned from dozens of different images. So it's an even cleaner and better representation of the original structure. And then you can use that MakeTran calculated reference area again to process the original image, unbend it better than you could do either with a small area from the middle or from the average of the whole area. And then you've more or less extracted everything that you can possibly extract from the original micrograph. And again, you combine them and you get your 3D model. So these are the three sort of levels. And I think this diagram gives you a kind of overview of what we do. So obviously, you can't go into too much detail. So I'm going to give you some snapshots of the different steps that are involved in that diagram in the next. So the MRC programs, again, the philosophy there was not to structure it into a single package that you press the button and go. We wanted to look at different stages to see whether it had worked. And there is a paper published in the Journal of Structural Biology 1996 by Jude Short, as she is now, and Tony Crowther and I, which gave a description of all the programs that are still in the MRC package, and we still send them out periodically to people when they ask for them. And these were the ones that were involved in the 2D crystallography, and these were the general purpose, these were the ones involved in the electron diffraction processing according to the system that we have that still works. And so far in Cambridge, we've used it on 3 different crystal forms of bacteria rhodopsin in 3D, 3 different crystal forms of rhodopsin, sort of bovine and frog, 1 halorhodopsin, and then Iban, I think, is the most recent person who took it through to a full 3D structure, which was EMRE structure. And then most recently, Vinos Kumar has been using it on 2D crystals of rhomboid, and I'll talk to Ivan about this a little bit later. So anyway, that's the list, and this is what they were originally called or had reached by 1996. But obviously, they've been continued to be changed, modified, debugged, and developed. And in the year 2000, we had a different set of subroutines for plotting out the results. So you get this nice graphical output. And that was called Plot 2000 or Plot 2K. So when we had a K on it, that means it usually has some plotting involved with it. And so CC Unbend, the unbending program, is now called CC Unbend K. And then others had A. So anyway, that's just a sort of overview of it. And these were the ones that were general purpose programs that people still use, including XIMDISP, which is the sort of MRC equivalent of Web or Imagic or EMAN and so on. Okay, so this was our original simplified flow diagram. And I'm showing this because I'm just going to show you 2 or 3 slides from that paper. The idea was to record the images, select good ones, scan them, do that cross-correlation map that I just described, find the distortions with the searching for the cross-correlation peaks, unbend it, calculate the Fourier transforms, and then after you've done that, determine the contrast transfer function, and we have a program called CTF search, and then CTF apply corrects for it. Beam tilt was built in from 1984 as a simple flag. You just say, do I want beam tilt to be determined or not? And then it will determine it against all previous images in the stack or against a merged 3D data set. And similarly, the crystal tilt, if it's a 3D, uses the phases to find a gradient of an R factor, and then it refines the crystal tilt. And again, the better your 3D model, the better these different parameters are. And then you put lots of images in and get the structure by doing that. These were the first 3 images of purple membrane that we got about 1985, which are, this one was the only image we got from the EMBL. Jean Le Paul had a Zeiss microscope with a Siemens liquid helium lens on it. It was very unstable, and it would go wrong every hour and so on. And we gave up correcting the astigmatism because it was so annoying. So as a result, we have this beautiful image that goes out to 3.5 angstroms, but it happens to be more or less in focus with several thousand angstroms of astigmatism, which is why you get these nice. So this is the original diffraction pattern. This is the processed image with the spots that have been detected by MMBox algorithm. This was an image, when we were doing this, Bob Glazer was visiting for a year on sabbatical, and he persuaded Ken Downing to take a few micrographs on their minus 100 degrees centigrade. It wasn't very cold. They had bad vacuum problems, but it was partly cold, but it was a field emission gun microscope. And Ken sent this one image, which also turned out to be very good. So that was included. And then eventually, Fritz Semlin in Berlin got their microscope to be reliable, and this is one of the very first. So we had these 3 images, different degrees of astigmatism and defocus and so on, 3 different microscopes, and they were merged together really nicely in this 1986 paper where we were doing this sort of thing for the first. So this is the unbend. So it was actually a square area, but we've taken this. So the reference area was cut out of the middle, and you can see it's about 10 unit cells square. It's about 100 unit cells. So it's about the molecular weight of that bit that was being used in the unbending is about 10 megadaltons. So 1 unit cell is 3 molecules, so it's about 100 megadaltons. So 100 unit cells is about 10 megadaltons. And we're using 10 megadaltons to cross-correlate the whole micrograph and find where the unit cells are. And this is the height of the cross-correlation peaks. And obviously it's highest in the middle because you're cross-correlating not just the molecules, but also the noise that's been averaged by a little bit of filtering. And then this next one is the distortions from a perfect lattice plotted out. And obviously in the middle, where you start from, the central point has no 0 and 0, and then as you go out, it gets more distorted. And they're of the order of 0.5% of this, so it's a pretty good crystal. So then we used to fit, although in the end, it sometimes made it better, sometimes didn't. We used to fit a continuous sort of elastic function involving a bicubic spline with knots, and it came out on a square lattice, and if you subtracted the 2, you could see how well you'd corrected it for. But you were essentially not allowing sharp transitions. But of course, some crystals have cracks in them, and you want sharp transitions. So in fact, in the end, this smoothing and so on was only used in some of the pictures. So when you do this, obviously, the bigger the area, the more distortions and the more blurry the spots are. And at low resolution, of course, the spots are quite strong. But you can see that as a result of this, putting all the unit cells into the right place, we found something like a factor of 3 improvement and a much sharper. This is the average of all the diffraction spots. So there'd be about 100 out to 7 angstroms. So about 35 unique ones, and then there's 3 of them. But at higher resolution, of course, the blurring is the same, but the effect in terms of that it's further out in reciprocal space, it's a bigger, so you get a bigger improvement here. So the background is 7, so this peak is 10. So you've got about 4 or 5-fold improvement here. And then beyond 5.5 angstroms, so out to 3.5 angstroms, you couldn't see anything at all in the original images. But after you did the unbending, you've got something like a signal of 10, so 1.5 times the background on average. So some of the spots are very much stronger. And if you pick the spots that you know from electron diffraction to be strong, you could get this peak at 3.5 to 5 to be stronger, and then you see a little bit in the untreated image in the beginning. So you've got about a factor of 10 improvement in the signal to noise. And that's just looking at the spots. And the thing I should also emphasize is that in order to be confident that we were doing the right thing and not somehow or other reinforcing noise, which is a big problem in single particles, because you don't have this spot with background around it. All the unbending was done on that originally filtered image, and we only used spots you could see in the original optical or computed diffraction pattern. So in fact, there was nothing in the unbending procedure that used any Fourier component beyond about 6.5 or 7 angstroms resolution. So these spots here at high resolution were never included in the unbending. So the fact that you see these getting stronger immediately proves that you're doing the right thing. And from then on, you're confident that everything that you're going to get is the real structure. And absolutely opposite holds with single particle EM, because you have no spot and background. And when you put it together, you're refining it together into a self-consistent structure. And it might be right and it might not be right. And so one of the challenges in single particle is to develop the same kinds of signal to noise criteria where you have some of the information from your images is left out of the processing, and you can look at it and be absolutely assured that you've done it right. And so almost before you start merging and calculating the structures, you know you're onto a good thing and you know you're doing it right. So what we hadn't got at this point was the beam tilt. Beam tilt will be on the next slide. What we did was to take these amplitudes that you get in the images and compare them to the electron diffraction pattern. I think we already had Carsten showed a slide like this. And this is a couple of typical images plotting the resolution against the amplitude of the image component compared to, and you can see that they fade out in the images compared to the electron diffraction pattern. This is natural log units. So that's 4.5 natural log units, something like more than a factor of 100. So these spots out here at 4 angstrom resolution are 100 times or several hundred times weaker in amplitude than they should be. And that's 10,000 times weaker in intensity. They're very weak, but you can still see them. And you can see it's not a straight line. This one curves down, this one's nearer to straight. But we're plotting it against resolution and not resolution squared. And typically in X-ray crystallography or in thermal disorder, you should be plotting this against resolution squared for a log curve to be linear. And if you do that, it actually curves upwards. So there's something about these images. Probably they contain a high resolution component that goes out to high resolution, and then there's more at low resolution that's sort of separate. So it isn't behaving as a single Gaussian. It's more complicated than that. But it's interesting and useful to do that because it tells you something about what you're doing. And then the next slide shows this business about beam tilt. And the original way, so what happened was in these unbent micrographs, we got these spots. You could see them. You could read off the phase, and you'd make a list of the phases, and they didn't agree at all. They were completely random numbers, actually. And what that showed was that it's very important to have good enough diagnostic techniques that you can prove that what you're doing is right. Because before all this work was done, there's another paper that not many people have read, and it's best forgotten, except as a lesson. And it was Steve Hayward and Bob Stroud. They thought they could process images of cryomicroscope images of bacteria rhodopsin because they thought they knew what the amplitudes should be. And so they assumed that the images would be having a signal, but it was below the noise level, and they averaged them, and they published a paper called Projection Structure of Bacteria Rhodopsin at 3.5 angstroms or so on in GEMB in 1983. And it's all complete rubbish. And the reason was they didn't ask, could I be wrong? They assumed they were right. And that is partly happening in the single particle EM world at the moment with some of the papers. So what happened is we came along and we looked at the phases because we'd unbent them. We could see them, and they didn't agree at all. And we thought, well, have we got the spherical aberration wrong? Is there some pincushion distortion? We tried dozens of things. And it was this plot that showed it. So we're plotting against resolution squared. We're plotting the position of the phase origin in refining the symmetry of that crystal. And we're doing it in resolution zones. So at low resolution, the phase origin is here. You can think of this in position. And it's actually the phase shift in degrees for the 1O reflection. So this 20 degrees would be like 1/20th of the unit cell. So it would be about 2 or 3. This is about a 2 or 3 angstrom movement of the origin. So at low resolution, you have it here. And if you only use the high resolution spots to refine the phase origin, it's moved by about 3 angstroms. And obviously, a 3 angstrom Fourier component, you've gone once completely around the phase circle. So naturally enough, it was rubbish. And it turns out some of them were twice round the phase circle. And this was a 2 or 3 milliradian beam tilt. And it fits on a nice straight line. And when you look into the beam tilt theory, there are 2 papers. Fritz Zemlin has one in 1978, showing that this is terribly important. And this is how the Zemlin tableau came up. And this is now all programmed into the microscope. So you have now coma-free alignment, and you just turn the knobs, and it does it. And hopefully, provided you haven't changed the height, or hopefully it stays in your. But still, it's useful to check that that's true. But when this work was done, of course, that wasn't easy to do. And actually, we were working with Fritz, and he didn't tell us about this. And what happened is a paper in 1983, David Smith et al., and it's entitled "The Importance of Beam Tilt Correction in High-Resolution Light Microscopes," and it refers to the Zemlin paper. So there are these 2 papers, 78, 83, and then we included it in our software as a sort of automatic correction. And when you do that, all these spots that each of them had an individual amplitude phase, you could see them. This is at 4.7 angstrom. You can see all the different measurements of that one spot's phase, and the length is proportional signal to noise. You can see they all agree quite well. And this was roughly the highest resolution we got. There's nothing, everything is within 180 degrees, and you average them and you get quite a good result. And then you do that for a dozen micrographs. This is the one from Heidelberg, this is the one from Ken Downing, and all the others were from Berlin. And you can see the amount of beam tilt is from 1.5 to 3.5 millirad. We had nothing that was 0 or 0.5. And it's thought that with coma-free alignment, you can get it down to 0.3 or 0.5. And once you're down to about 0.1 or 0.2, you're fine. You don't need to worry about it. But you probably ought to check it, because it's not enough to think your beam tilt is 0.1 to 0.2. You ought to somehow or other use the data from the images to prove that. And if you're doing 2D crystals and merging using MRC or sort of subsequent software, those numbers will be checked, and you'll be able to tell how good they are. So this was our best ever purple membrane untilted image that Fritz Zemlin took in Berlin, and it goes out to 2.8 angstroms. And in order to know what we were doing and to be able to hold in your head what's happening to all your different micrographs, we created summary sheets like this, which I think is still a good idea, particularly if it's a new project. So you can see this is quite an old one. So the idea was you write down everything about it, but you have data that proves what you. So this would be the first pass, and this would be the second pass in terms of the unbending. And we had the defocus, the astigmatism, and so on and so on. And H is the height of that peak in the middle of that box 9 by 9, with the background adjusted to be about 7. And you can see that we've got, with a background of 7, we've got a signal of 3,000 at 7 angstroms, 300 at 5 angstroms, and even this got up to over 100. So the average of all the spots out to 3.5 at the high resolution is something like 15 times the background. So, and actually we thought this was such a good image, we did process it out to 2.7 or 2.8 angstroms. And then we also had cross-correlation between the amplitudes of these diffraction spots and similar data from electron diffraction. And you can see the numbers are 0.9. It's a very good image. But if it's a weak image or a noisy image, these numbers would be smaller. And if it was rubbish, cross-correlation would be 0, and this would be 7, which would be the same as the background. So it allows you at a glance to see how well you're doing are you making progress or are you regressing, in which case you should stop and go back to your last good pass. And so you can judge how good is your image, how good is your computer processing, and you immediately have a feel for how well you're doing, and it's reliable. Okay, so that's untilted. So here is, if your image is tilted, this is the height in the specimen, so that's one side of your image, and here is the other side, maybe a micron different in height. And because the defocus is changing, and in the contrast transfer function formula for sine chi is proportional to delta f theta squared, where theta is the diffraction angle. I think Carsten had it as alpha. So if the height is changing across the image, the delta f is changing. And if you look at one spot, delta f theta squared increases, and the sine of it goes like this. So as you go across the image, the contrast for a particular Fourier component goes linearly from positive to negative, and so on, across the image. And if you simply average it, there'll be nothing at that Fourier component's exact position, because you'll have an equal number of positive and negative spots. And if you look at it in the electron diffraction pattern, you had your diffraction spot, but you've multiplied by this contrast transfer, or tilt transfer function, as we called it. You multiply the projection by the tilt transfer function, and its Fourier transform is then the convolution of your original Fourier component of the image, which would be a spot at that position, with the Fourier transform of this, which is three sine waves, and that then creates a peak at +3 and -3 pixels, because you've got 3 Fourier components across it. So instead of seeing your nice diffraction spot, it's split into the 2 Fourier components. And another way of thinking of that is that you've tilted your crystal, and the 2 diffraction spots come out, they've been moved slightly because the intersection of the reciprocal lattice with the E-volt sphere, the geometry moves them slightly, and it's exactly the same thing that's happening, but it's 2 different, let's say, theoretical ways of following it through what's happening. This way is a convolution way, where you get it split. The other way is intersection of spots in the E-volt sphere construction, which have a different Fourier space, and they interfere with the direct beam, and you get these 2. So they're actually, these 2 split spots come from the 2 diffraction spots that come out from your crystal, from the specimen. Beam comes down, specimen, diffraction spots out, E-volt sphere, one is slightly different from the other, they interfere with the direct beam, and you've got the split spots. And provided your crystal is relatively thin and your voltage is high enough, these are more or less the same Fourier components. So in our original programs, the way we corrected for them, this is TT box, TT refine, and TT mask. You multiply the original image by the tilt transfer function in that region of reciprocal space, and essentially correct the contrast by multiplying the same function in the computer by the same function that happened in the microscope. And this is what you end up with. So everything is correct, but where you had a 0, and therefore you only had noise, you're also multiplying by 0. So in a way, it's correcting the signal to noise in the image as well. And then the Fourier transform of that brings you back your correct amplitude and phase in the correct position, and you get those 2 wings, which are artifacts of the fact the way you've done it, and you ignore those. They don't contain any more information. It's the same information that was there in the beginning. And in that slide that Carsten showed, where he showed a correction, he had, let's say, ghosts outside of the real corrected structure, his little checker square thing that had been moved out. That's essentially the same kind of thing. Okay, so when you then look at what happens to a real image, here is a particular tilted image of a tilted diffraction 2D crystal. Here is what one of the spots looks like. This is the 2-4 reflection at about 10 angstrom resolution in a 45-degree tilted image. Here is what it looks like before you unbend it. You unbend it, you get the 2 spots you expect, because we're not correcting for the contrast transfer function. After we correct for it using the TTF, you get the correct spot with the correct phase in the middle, and you get these 2 wings, which are a little bit further out, twice as far out as these ones are. And then looking at a higher resolution spot, of course, there's nothing in the image because it's all blurred out and it's weaker. But after you've unbent it and corrected it, you can see the two split. And they're split more because it's a higher resolution. And after the tilt transfer function, you get the correct amplitude and phase, and then the ghosts that you ignore. And how does it look like in the unbending? So here is this top right-hand panel. Again, we've picked a little bit in the middle of the crystal as the reference area and used that to unbend the whole thing. And this is the peak height. And of course, because at the beginning, this has got a certain defocus and so on that we don't really know and so on. It agrees best with the bit of the image near it and at the same defocus level. And as you go nearer focus and further from focus, some of the Fourier components are not right, so you get lower correlation. But it's enough to get started, and these are the distortions. So you use the reference area to unbend the image, just like I showed on that first slide. And then you've unbent it, you correct it better, and then you average the whole image and get a much better corrected reference area. And then you do the unbending again, which is bottom right here. And so the reference here was about 100 unit cells in the middle. The reference here is the whole area, properly averaged and corrected for all the phases. And so what you then get is cross-correlation peaks. And as you go, this is basically almost in focus. So you have almost no contrast there, or only at very high resolution. So the peaks are very weak. And as you go to bigger and bigger defocus, the contrast transfer function moves to lower and lower resolution. You have stronger spots. And so you get stronger peaks, not necessarily more accurately positioned, but stronger. And again, you unbend it, and then you get a better result in the end. And this was a 45-degree tilted image near the tilt axis and far from the tilt axis. And of course, it depends on your transform and how flat your crystal is and so on. And this is after unbending, and you can see that. And again, we're using only the spots out to 7 angstroms to create the reference image to do the unbending. And so there's nothing in the whole procedure that looks at anything beyond about 6.5 or 7 angstroms. So these spots here are a proof that you've done it all quite nicely and correctly. And obviously, along the tilt axis, they're sharper. The lack of flatness doesn't affect the ones near the tilt axis because they're not far up in Z. So they tend to be sharp. And also the Fourier transform in the case of a membrane protein tends to be strong in the plane because you've got alpha helices vertically or beta sheets vertically. And then this is along the tilt axis, so it's weaker there. But you can see it's still quite significant. So then this is the same sort of summary diagram that we used for the tilted pictures. And again, it's vintage 20 years. So here is 4 passes of the unbending procedure. And this number H, that's the height in the middle of that 9x9 box. And you can see when we started, near the tilt axis, we had a height of 25, still way above the noise, but 8, which is barely above the noise, perpendicular to the tilt axis. But as we learn about the defocus, and you can see it's being changed slightly, and you learn about the unbending and so on, it goes up from 25 to 41 to 43 to 47, 23, 27, 26, 20. So, 8, 13, and then 16. And then we stop here. Actually, we usually do others, but if it doesn't get better, you go back to your one where it was the best. And so you end up with a complete list of spots, and you're sure that on average they're really good. Some of them will be very good, some of them will be at near noise level, and again you have this cross-correlation. You can see here that at the highest resolution, 3.5 to 5.5 angstroms, the cross-correlation with the electron diffraction has dropped to about 50% on average. So I have to say these two, the 2 examples I've shown you, they were the best 2 pictures. So you can still use them when they're a lot worse than that. Okay, so that actually is what Holger Henning asked me to focus on. And so that's the sort of tutorial bit with a historical emphasis. And of course, I can answer questions about it. But I have an equal number of slides that's supposed to give you a feeling for things and not too taxing intellectually. So I'll just carry on with it. So this is what was it that allowed us to go from sort of lowest resolution, where we weren't doing unbending, we weren't doing beam tilt correction, we weren't doing lots of other things. So around in about the 80s, these were some of the factors, and they're still relevant for, if you've got a new protein, a new crystal, you want to know what to do. What is it that makes it better? Well, obviously, the bigger the crystals, the better. And one of the things, if you're doing electron diffraction, you do get better electron diffraction patterns when they're bigger, although there are some pitfalls I'll come to. So we made, in the case of bacteria, we recrystallized it either by fusion or by dissolving it and then dialyzing detergent away. And then we didn't have cold stages until about 1985 that had high vacuum, and they came in through Jean Le Paul and Jacques Dubochet in Heidelberg, Fritz Semlin, and Ken Downing, and so on. And now you buy them, and they are wonderful compared to the old ones. Unbending, but there are other ways you can do it. Beam tilt, you must do that, beyond about 5 or 6 angstroms. The tilt transfer function is just a programming thing. And then the field emission guns, Ken Downing had one, but you couldn't really buy them until about the mid-80s, and then not everybody had them at the beginning. But they were the things that really made a difference. So now there's a kind of giving you a feel for, this is a map Nigel Unwin and I calculated in 1975 on a 100 kV room temperature microscope without any freezing. And the spots are only about 5 times stronger. You only get a factor of 5 by going to liquid nitrogen, but it makes a fantastic difference. So that's why now, if we talk about having another factor of 2 here and 2 there, another factor of 5 will make an equally big difference, actually, and particularly the high-resolution single particle. We need to go for these apparently small factors. But anyway, so that was the 7, 1, 2, 3, 4, 5, 6, and these were almost unresolved. But there were 7 transmembrane helices. By 1984, again, without any cryo, we'd had multiple crystal forms. We tried to do averaging, model building, and so on. Joyce Baldwin made this map in 1984, and actually we didn't believe it and didn't publish it, but that big blob there is the beta ion ring of the retinal, as we later found out. And then cryo came in, and by 89 we had some beginnings of side chains, including this very big density, which is the beta. And then eventually, when we published our first atomic interpretation, you could see in 1990 we had lots of side chains, phenylalanine, tyrosine, tryptophan, and the beta ion ring. But there's not. It's a factor of 2 in resolution, so 2 times 2 times 2. It's about 8 times, 10 times in data. But it did take 15 years or something like that. So the single particle stuff is now somewhere in the middle here. But obviously with technical improvements, it's going to get to be quite good as well. Okay, so a few more to flick through. That was when CCDs came in, and you could subtract the background, and you could get better signal to noise than on film, and these spots go out to nearly 2 angstroms here. This is an optical diffraction pattern. That was the same comparison that Karsten showed. Electron diffraction on the right, optical diffraction on the left, and you can see they fade out more quickly. This is a slide I made as a tutorial for what we do when we do image processing. This is the raw image. These are all on the same scale. Well, I'll explain it. This is the raw image. After you've indexed it, unbent it, and so on, filtered it, that is the signal on the bottom on the same scale as the raw image. So you can see that the signal from the 2D crystals, if it's a thin crystal that's a membrane protein and so on, isn't very high. It's about 10 times less than the noise. Obviously, if it's a big one, and it sticks out like P-type ATP is and so on, you have a bigger signal. You will be able to see the molecules in the raw image of the crystal. So what we've done here is we multiply it by 10 to bring it onto the same scale, but you can see it's not recognizable. This is the CTF correction of the image, and so now you can see the molecules, and then we add in the proper electron diffraction intensities, which don't have zeros in the CTF, and do threefold averaging, and that then is a more or less perfect noise-free projection structure of the molecule. And you then apply it to the whole crystal, and that's a pixel thing in the middle. You can then make a contour map, and then that's one molecule, and you can look at it bigger. And then in 3D, I think this is our sort of, the traditional X-ray crystallographers use ducks, even though they have symmetry. It should really be a duck looking to the right. And then you combine it by, central section 3D. And this is some examples of electron diffraction, which I'm not going to talk about, two particular spots in bacteriodopsin as you tilt. And you can see the diffraction, the Fourier components coming and going, different Fourier components. And the big peaks at 5 angstroms come from the fact that it's helices, and they have about a 5 angstrom pitch. So here is the diffraction. Here are all of the lattice lines averaged, untilted, and we only went up to 60 degrees. And the 5 angstrom axial is here, so you miss quite a lot of it. This would be the 10 angstrom helical packing, and then this is the 3 to 4 angstrom side chain packing. That was the same map I showed you before, phenylalanine. So, and then here's the model-fitted phenylalanine, tyrosine, tryptophan, and beta-ion ring, which gave a atomic model and sort of schematic, some mechanistic things. And then Sriram Subramaniam worked for quite a while on different trapping of different intermediates, different mutants. And this was, purple is the wild type, and yellow is a particular triple mutant of bacteriodopsin, which adopts a conformation that's more or less the same as the one that's at the midpoint of the light-driven photocycle, and it involves about a 3 or 4 angstrom movement of the top halves of the 6th and 7th helices. And this is a structural change that has never been seen in 3D crystals made for X-ray crystallography, because the lattice stops that movement happening. You only see it in the isolated 2D membrane fragments. And so that's another plus point and a reason for perhaps doing both. If you've got a really good protein preparation, make 3D crystals, make 2D crystals, and do both. Was a list of, and I think you'll have seen, this is the Aquaporin Zero sort of champion. Okay, so then I thought I'd just do 2 or 3 things. What are the problems to keep an eye out for? So one is getting the space group right. Another one is being aware that your crystals might be twinned. In X-ray crystallography, people are very aware of this. In the 2D crystallography, people are less aware of it. And then, what useful things come out of comparing to X-ray? So there's 2 or 3. So this is the same 17 space groups that we heard about just before coffee. And I think it's useful to have, one convention is that 3D space groups use a capital letter here, whereas the 2D, either the plane groups or the two-sided plane groups, the sort of space groups, use a small symbol. So I think we've stuck to that. And I think I would advocate that if you say, so two-sided plane groups, there are 80 of them, but 63 of them have got symmetry that you don't get in proteins, and only 17 of them are these chiral structures, and these are the 17, except P622 is off the bottom. The equivalent ones in 3D are more or less the same, although they have different axes that they pick sometimes with the convention. But the only difference is that usually we use 2D with a small p and 3D with a big P. And the difference is, obviously, the plane group is the same in some cases, but P21 means there's no symmetry other than a twofold along Z, and the M is replaced by a twofold in the plane. And this is, so the first time I think it was described for the 2D plane groups is this reference, Holzer, Zeitschrift for Crystallography in Germany in 1958, and that's the same nomenclature that we had from earlier. And then Allspace, if you read the header of it, these are the symmetries that it applies. It's just a matrix, and it runs all 17 of them, or if you tell it you think it's a square lattice, it'll only do the square ones, or hexagonal, do the hexagonal one. So here's a halorhodopsin crystal. Here are the spots. They've been already corrected for the CTF by looking at the zeros in the transform and refining it, possibly starting with CTF tilt, CTF find first, and then refining it using CTF search or something like that. But anyway, you get then out of this a list of amplitudes and phases corrected for the symmetry, and you then ask what is the space group, and then you run Allspace, and Allspace should only be run on untilted pictures. Otherwise, it'll work, but it'll just give you random numbers. And the table that was left off before, so the last column is quite an important one. So in our MM box, TD box, when you read out the amplitude and phase of each spot, you get a signal-to-noise ratio. And we encoded that as this IQ value, which is 7 means it's got a signal-to-noise ratio of 1, and 1 means it's a signal-to-noise ratio of 7. And it was to try and kind of distribute them more evenly. But you get a signal-to-noise ratio, and from that, you can predict the phase error of every measurement of phase, in theory, from the signal-to-noise ratio of that spot. So what AllSpace does, it takes that value of IQ, or the signal-to-noise, and it calculates what the phase residual ought to be if you've done everything correct, if you've done beam tilt, CTF correction, and so on, and you've got the space group symmetry right. It tells you what it ought to be, and it then compares what it is when you assume particular space groups with what it, and then of course it could be slightly tilted, and it could be, and then it gives you this symbol, which is it's acceptable if it's within, I think it's 1 degree of that, and you can see here all the symmetries for halorhodopsin, which actually the space group is P4212. You get a 28-degree phase residual for all the spots that were used, compared, so it's better than you expect from the signal-to-noise ratio. And then, of course, all subsymmetries also work, because P4212 has a 4-fold axis, so it is equally compatible with P4, or with P121, and so on. So you get the symmetry and all the subsymmetries. And because you've carried through this signal-to-noise ratio, if this number is less than that number, that means the space group must be that symmetry. Or it could be higher, or of course it could be only to that resolution. There are some limitations, but I think it does sort of prove it. So it gives you a kind of reliable indicator. In other words, if you get a star here, then you've basically succeeded and you can relax. Referees shouldn't be able to criticize you, except, of course, if you indexed it wrong or left out, and I'll show you a little bit in a moment. So here was an example. This is halorhodopsin. Go back to this. At low resolution, you don't see all the spots. Every other one is weak or missing. And when we first did this, we said, oh, well, we can ignore those intermediate spots. It's some kind of perturbation, doubling of the lattice, and so on. And so we ignored them. And actually, we got the wrong space group, and we submitted the paper, argued with the referees, and it was in press. When we decided we better look at these spots. And it turned out, the cell dimension, this is what we'd got. And we thought it was 2 layers with a small unit cell and some perturbation. Actually, this is the real unit cell. And the molecule is there, and the 4-fold arrangement of the 4 molecules is very similar to the upside-down 4-fold, and that's what causes the spots. So it's a kind of, so this is the proper space group, P4212, and this one, which was 422 with a smaller cell dimension, is wrong. And you can see this is bacteriodopsin, halorhodopsin. They are homologous, 30 or 40% homologous. So we did actually, by having AllSpace, we managed to correct our. We put all the weak spots in and got the right space group, and then sort of retracted it and resubmitted it. So we avoided having our reputation shredded. And so okay, so a couple of other problems. One is twinning. So here is here's a 2D crystal of bacteriodopsin, bigger than the normal one, and here is an electron diffraction pattern, slightly defocused. And if you look at each spot, it's got a strong bit and a weak bit. And then the mirror symmetry is 4-3 and 3-4, a weak bit and a strong bit. So what's happening here? So what's happening is this crystal is 2 crystals. And this crystal is like this, P3, and this one is upside down. And because all the molecules are in rows, they line up and you get a perfect twin boundary. It's exactly the same as in 3D crystals. And if you just put all the data in together, you get the wrong amplitudes and the wrong phases and so on. So you have to be aware that might happen. And then here's another example. This is 4-fold twinning. So P3, you can have a 2-fold axis twinning it, turning it upside down. You can also rotate it by 180 degrees. And there isn't 180 degrees, it's only a 3-fold. So that's called tetrahedral twinning, 4-way twinning. And then each crystal, you diffract it, you get spots. Actually, they look nicer because since you've got the average of 4 different orientations of the crystal, all the spots which were weak before, because there's a 0 there, they get replaced by a bit of one crystal, a bit of another. You have average. So actually, they all look rather more even And somehow you think you pick them out. These ones are better, but actually they're worse. And this was a particular double mutant, which is rather unstable, and you couldn't ever get big coherent areas. So what we did is we used make-tran when we did the 4 different orientations, and we unbent it. And these are the cross correlations from the unbending of the same image with 4 different orientations of the unit cell. And what it shows is that this area is, let's say, the main component. This one is the same as that, but upside down. And these 2 are upside down rotated and the same way around. And you can see they all fit together beautifully into a mosaic because it's a single layer of the crystal. And if you had processed it as a single coherent average, then all your Fourier components would be the average of the amplitude and phases of 4 different spots, unrelated. Twinning is something that's worth keeping in mind, actually. And one way of doing that, of course, is to do multivariate statistics on all the unit cells, because it will pick them out without you having to specifically test for them. That was just a superposition of 2 EM and 4 X-ray bacteriodopsin coordinates. Yoshi's group in Japan quite independently repeated all the imaging and all the electron diffraction and got a completely independent 3D structure, model built and refined from what we had. All the X-ray people simply took the EM coordinates. So no X-ray structure determination. There's been dozens of them now. There are 66 sets of coordinates in the database, and all the X-ray phases come from the EM maps originally. Of course, they've been polished up and refined, so now it's actually quite useful to take the coordinates back from the X-ray, and then so it's a kind of synergistic thing. And then another map is Eban's map with Chris Tate, and at the time this was published, which was 2003, it disagreed completely with the X-ray map, and it turned out the X-ray map was complete rubbish. So, this is another example where, it's quite useful if you've gone to all the trouble of purifying your protein and making crystals, and they make 2D and 3D, it's useful to at least do some work on both of them. That was the same plot showing how things have been fading out with different B factors. This was room temperature data, early liquid helium. This was that best image we had. And if you convert that into an equivalent B factor, which is amplitudes equal what they should be times the exponential of minus B over 4D squared, that's more or less that line, more or less. And that's about as well as you can do, about 120. So, but you're down here by, this is about a factor of 10, this is down by a factor of 50. So this means the amplitude here at 3 angstroms is 50 times less than the electron diffraction patterns predicted it should be. And if we could fix that, you'd be able to do so much better. So we have actually, and this is the last thing I was going to say, we've tried working on ways of imaging 2D crystals and single particles. But now we think we understand one of the problems with why it's so bad. And basically it's when you put the beam on, you create radiation damage. There is a bit of fading of the spots due to that. But mainly things move around. And so what we've done is to work with paraffin. And so here is a 2D crystal. This is paraffin on one side of the carbon, paraffin on the other side of the carbon. This is an early one, Bob Glaser, when he came on that year of sabbatical. That's a demagnified image. That's an electron diffraction pattern. These spots are at sort of 3.7, 4.1 angstroms. So this is the first spot in paraffin is basically at the same resolution as the last spot that you'd be happy with in X. So it's a very good sample. And these spots here are 1% of the intensity of the direct beam, 10% of the amplitude. So it's a very, very good thing to, if you take a picture of paraffin, you have to be very bad not to get a spot at 4 angstroms, So this is the same electron diffraction pattern, again defocused, and you can see these little fragments. We put the beam on it roughly on here. So that is, and this is the edge of a grid bar actually. So that's the little triangular crystal, and that little bit is that little bit in there. And then here's an image, optical or computed diffraction pattern of an image showing you the diffraction spots. And what we found was these spots are just as bad in terms of their intensity compared to what they should be as the images of the bacteriodopsin pattern were, a few percent. So we've worked at this And then this is a picture taken recently. And the last 3 slides is something we've just submitted. So here is a nice picture of paraffin, defocused bright field, with the beam illuminating it. And here is, if you change the gain level on the CCD that was looking at this, the direct beam is overloaded, and these are the diffraction spots defocused from these are the 4.1 and the 3.7 angstroms, or 3.7, 4.1. And if you fiddle with the slope of the gain, you can see the crystal and the diffraction spots in the same picture. So that's all electron diffraction. You then take an image of this and calculate the Fourier transform, and here are the spots from the Fourier transform, the same indices, roughly the same orientation. You can cut out those spots in the Fourier transform, back transform it, and find out where the power in these image for one spot, where it came from, because it's so strong. So it's kind of like the cross-correlation map in the unbending. But what you see, and this is sort of a typical image on ordinary carbon film, it's not beautifully homogeneous over the whole image. There's good bits and there's really bad bits. And for one spot, the good bits and the bad bits are different from another spot. Here's the 2O, 1, 1, and -1, and this is all of them together. So there's a bad bit of the crystal, but yet if you look at the electron diffraction pattern, it's perfectly oriented, it's not tilted, every part of it is beautiful. And you look afterwards and it's just the same, apart from the bit where you've burned it. So what's happening is that the image is moving around and blurring it, and the same thing that causes the intensities to fade in the diffraction pattern, the blurring, is what you see here. So we've spent years trying to get this to be fixed. And one of the things we tried is spot scanning, and that makes definitely an improvement because you're only illuminating little areas at a time. And we also had this Medipix zero noise detector, so you could take, instead of one image, you take 400 images. Shouldn't be moving. And we found both of them improved it. But the one thing that for 2D crystals seems to absolutely solve it is you just use extremely thick carbon. So we made a carbon of about 350 angstroms thick, and it doesn't. So here is not quite such a nice crystal. It's got the places where we were focusing sort of burnt out of it. But there is the bright field. There is the dark field. You can see that it's quite nicely oriented. Here is the calculated diffraction pattern. Now let me just get this right. So this is before we took the high resolution image. You can see it's nicely illuminated, and this is the high resolution computed diffraction pattern. And this is the electron diffraction pattern taken. This is before and after that image was taken. And you can just see where the beam is circular, and you can see the edge of it in that spot. And it's actually in all of them. So we've burnt away about a third of the diffraction power. So the diffraction spots have faded to about 2/3 of their intensity. But it's still perfectly well oriented, so it ought to be perfect everywhere. And because we had it on thin carbon, and then we burnt it all away to show where the beam really was, and you can see it's burnt this circular hole. And these are the diffraction. These are the pseudo dark fields where you cut out one spot, back transform, and find where did the power for that spot come from. And you can see it includes one of these little bits that are burnt in the crystal. But it's fairly homogeneous for the 1-1, fairly homogeneous for the 2-0. And then, of course, there's a 0 because it might have a defocus 0 or a beam tilt 0 or so on. But actually, it's pretty homogeneous. And then the final thing is this rather complicated. This is something like 10 images that we've taken. And we calculate through all the amplitudes, compare them to electron diffraction pattern, correct them for the detector. And you can see some of the ones at the beginning aren't so good. But the bottom ones, we've more or less got, not every spot, because there's a defocus and the beam tilt and so on, but we've more or less got it to be perfect. In other words, we've got an image now which, by analysis and understanding what's going on, we think is a more or less perfect image of a paraffin crystal. And with high voltage microscopes now, 300 kV, you can use quite thick carbon, and it doesn't really affect you. So our message for 2D crystals is 300 kV and thick carbon. And obviously, having the sandwich method might help to keep it flat and so on. But of course, that's only on paraffin, and that's something that we've just been doing. So let me just finish now. I mentioned tilt transfer function, that you can get a better reference with MakeTran. I'm going to show you one more slide about the size of the reference box. Thick carbon is very good. Obviously, it has to be flat. Single molecules, Henning mentioned. And then the two things that are not quite into the single particle work yet are beam tilt. And then, of course, when you unbend it to the lattice. And if you've got, let's say, differential magnification, often in the microscope, the magnification in this direction isn't quite 1. It could be 1.005 or something, 0.5% difference. And then your molecules are stretched by 0.5%. So when you rotate them, they don't average without. And of course, that's all taken care of in the 2D crystal. You don't need to worry about it. So this is, I think, this is Nico's paper on deoxycholate bacteriopsin. So what he did is he reduced, and we'd done this also on the normal, he reduced the reference area from 300 pixels square, which is about 70 unit cells. So that's like 7 million Daltons is the reference area. He reduced it to smaller and smaller until it was 1 unit cell. So then it's like single particles, really. And that's the amount of averaging and so on and so on. And then he looked at, in these plots where 7 is around the edge and the box is the background, and with our typical way of processing it, you got something like 10. But as you reduced it and you did more unbending, it got better and better and better. And then until the area was too small, and then there's noise in it, and then it gets worse. And then when you go down to 1 unit cell, you've still created something better than an unprocessed image, but you're 10 times worse than optimal. So what that's showing is that 14 unit cells, about 1.5 megadaltons worth of reference, was optimal for the 2D crystal. But when you try and do it with 1 unit cell, which is basically 100 kilodaltons, and it's very strong because it's got all those helices, it's on the edge of being impossible. And I think the single particle images are not nearly as good as the 2D crystals, which are on thick carbon. And so for single particles, and this is what I thought I'd chat about this evening, we really need proper validation criteria for small things, say up to 1 megadalton. And then that was the acknowledgement. So obviously various people were collaborators during different stages of what I've kind of given you an overview of. And Nigel was the one who, so I used to be an X-ray crystallographer actually, till I met Nigel, and we thought it would be quite fun to try some EM. And we got this, and Joyce Baldwin, and these were the 3 people who had our original high-resolution images, wrote a lot of these early programs. And Tom Seska then recollected really nice electron diffraction data. And then Nico came in probably 15 years ago and did some refinement. Edmund Kunji developed this HR MakeTran unbending method. Okay, so thank you very much.
Thank you very much for a great talk. Unfortunately, I think you're already running a little late, so perhaps some few questions online.
So I think most of us came here for this, go around the globe for this. I think it's more important than lunch, my personal opinion. Anyways, I think we should just ask questions, right? And then here for lunch later. We can go to lunch also later, and we have more time in the afternoon. So I think this is the point of the workshop. So I think your result that thicker carbon helps, is that because of thinner carbon parafin jumps back and forth, or is it because you have evaporation strength in the carbon that is not so important as thicker carbon, which you could address with elephant annealing?
I think it probably does help to be very careful about the nature of the carbon film you create in the first place, particularly by measuring the conductivity. And, graphene is, I think it's 10 to the 6 ohm centimeters or so on, whereas carbon can be 1 or 0.1. It could be 1,000,000 times worse. So Nigel Unwin is the only one I know who's very careful about this, and he measures the conductivity. And if it's not, is it 10 to the minus 6 is graphene, and 10 to the minus 3 is, anyway, he throws them away. And we measured our films, and Nigel's are all 10 times higher conductivity than ours. And then the other thing you can do, you can irradiate them in the microscope before you put the specimen on, and that increases it by another factor of 4. So you're increasing the conductivity and the strength. But what we think we're doing with thick carbon is very strong. So compared to ice, it's got, Young's modulus 20 times higher. And 300 or 400 angstroms of carbon, it's just very strong. So you put the beam on your 2D crystals of your organic biological material, and it's damaged, and it's trying to move, but it's stuck to the carbon, and the carbon stops it from moving. So it's a kind of brute force method, whereas all our other clever methods, they make a difference, but this one was really quite a significant. And actually, in the early days, we tried various thicknesses of carbon, and we always found thick carbon was better. But in the 80s, we only had 100 kV microscopes, so you couldn't go too thick. So what we used to do is thin carbon for electron diffraction, where you're concerned about the inelastic background, but thick carbon for images, where the noise mainly comes from the direct beam, and it doesn't really matter about. You don't usually get, on a low-dose image, the tone rings from the carbon are often very weak. So even if you make the carbon thicker, it doesn't actually make much difference to the signal-to-noise ratio. And at 300 kV, with 400 angstroms of carbon, you've only got about 20-25% inelastic scatter or something like that. And actually, there are these now. Of course, if you have a lot of money, there is the CC corrector. And what the CC corrector, what that shows is that inelastic electrons are not scattered very much. The angle change isn't very much, and you can get perfectly good 3 angstrom resolution, high resolution images from phase contrast, from, obviously it's also elastically scattered, but from entirely energy, 100 electron volt energy loss electrons give you a 3 angstrom resolution image. So if you were to buy a CC corrector and have thick carbon and do 2D crystals and have high voltage, it would be, I'm sure all of the images will be better. So, that's our take on carbon. Sorry, Henning. Of course, when you tilt to 60 degrees, it gets twice as thick. So, but still, it would be a good idea, I think. I think what you'd gain from not moving is much bigger than you'd lose from this a little bit of extra inelastic electron. Because, the tomographers, they're using half micron. So, 400 angstroms of carbon tilted to 60 degrees, that's like 800 angstroms of carbon. That's like 1,600 angstroms of ice. That's still not too bad. That's right, yeah. I mean, the great danger with 2D crystals is they're noisy. You diffract them, you see spots, and you put it through this procedure, and you get the average of the whole crystal. And there's nothing in that procedure where you ever tested for twinning. Of course, twinning can only occur in certain space groups. You can't have twinning in P1, for example, because the cell dimensions, the angle is the same, so you rotate it. I suppose you can rotate it. You can rotate it by 180. It's usually in things with 4-fold, 3-fold, or 6-fold axes, where you can rotate it in the spots. You can flip the pattern, and the spots fall on top of the other spots, and then you get the average of them. And in fact, in 1983 or so, Linda Amos and Jim Dethridge did some early negative staining of sulfur-lobus cell wall. And they used this similar, before unbending and so on, but it would have been the same. And they published a 3D structure in Nature, space group P622. Later on, Baumeister, who actually had his earlier career, consisted of 3D reconstructions of 50 cell walls. So Jim Dethridge and Linda did this as a sort of side project, and there was some debate as to whether it ought to be published, but it was. But Baumeister came along, looked at the same cell wall, which came from Martinsried, actually, because they were working on it there, and took the 2D crystalline areas and put them into multivariate statistics and showed that on a very, very small scale, 2 or 3 unit cells, it was really not P6, but P3, the space group. And the little areas of the cell wall protein were rotated by 180 degrees. And so if you looked at a big area, even if it was negatively stained, it looked like it was P6, but actually it was P3. And so I think that's why, if it's a new structure and you're suspicious about it, for example, if it's a 3-fold, 6-fold, or 4-fold axes in your crystal, it's quite useful to divide up all the unit cells and put them into Spider or Magic and just see what happens. And it will be able to sort them, even though it's below the noise level, into the 2 pictures, that's what you'll be looking for. And until you do that, I think you could easily have missed it. So the Baumeister published a paper subsequently, about 5 or 6 years later, showing that it was really P3 and not P6. And then by picking out the unit cells and treating them separately and flipping them correctly, you got the real structure as opposed to a structure with some extra added symmetry that isn't really there in the real structure. And the 2 examples I showed are because we were aware of this. As soon as we did fusion, you fuse 2 membranes, they're as likely to go upside down as they are the same way up. So all our electron diffraction patterns were all D-twinned anyway, so we were kind of aware of that. And then it was only later that we started to look at it for images. And it was an interesting wrinkle on it, but it wasn't an important aspect of what we were doing. But it might be in other cases.
No more questions? We should thank again both speakers.